In this video I'm comparing a classic receiver, ft1000, with an SDR, a Perseus. I'm sending various strong signals through this cable into a notch filter. It's 3 kHz wide on 13.998 MHz. And it has a very good attenuation within that stop band. After the filter there is a 6 dB attenuator and a directional coupler into which I can send a reference signal in the center of the filter notch. Then the signal is split in this 3-port splitter, one into the ft1000, the other one into the Perseus, and the third goes to a spectrum analyzer where I can look at signal levels. At this moment the signals are switched off, there is only noise. This is the spectrum from the Perseus. It looks like this. There's nothing there. What we see in the S-meter graph is S over N, but the signal is just the noise in this 50 Hz wide filter. And I have set 53 in this box to make the signal to noise ratio become 0. Means the noise within this bandwidth is now calibrated to show 0 when it's compared to the noise power over this 2 kHz wide spectrum. The Perseus is set to 2 kHz bandwidth. The ft1000 doesn't look as nice. It's an analog receiver and it's not perfectly flat. Here is the passband and there is no signal. The close range centered around this green line looks like this, and I have selected exactly 2 kHz bandwidth from here to here, and I'm sending that into a second instance of Linrod where I do the signal to noise measurement, and I have selected a frequency at the center where the noise power is more or less the average of the noise power in the total 2 kHz width. I set the filter to exactly the same bandwidth, it's the same sampling rate, and I have fed the same number into here, and I then read 0 on the signal to noise graph. Now I can switch on a test signal, sending it in through the directional coupler, and I place that signal in the middle of the filter, this 50 Hz wide filter here, and I do the same for the Perseus. And then I look at the signal to noise ratio. It's about 30 dB, and as it happens it's close to 30 dB also in the ft1000. This means the two radios have similar noise figures. So this is the signal I send into the directional coupler. Here is another generator which is set to maximum level or near maximum, and here is another one. They are set to provide the same signal level into the test objects. The signal from these generators are amplified by 6 dB in these amplifiers, and then combined in a 2-port combiner, hybrid combiner. And the output from that is sent into this unit, which is a low-pass filter. It has a notch, but it's very narrow and doesn't affect measurements here. But this guarantees that no overtones are reaching the receivers. Overtones might mix with the fundamental and form second-order harmonics, second-order intermodulation, and that is a possible source of measurement errors. I now set the 2 strong signals until I see something like a 3 dB loss in the signal-to-noise ratio in the Yaesu ft1000. This is maybe 3 dB, maybe a little less. I increased the level by 1 dB, and now the degradation is more like 5 dB. So this is the point where the intermodulation, which we see here, is strong enough to degrade the signal-to-noise ratio by 3 dB in the ft1000. The signal levels for that is minus, and I'm running this unit in IP0, means when it's not so sensitive to intermodulation, but there is no attenuator. So it has then the same sensitivity as the Perseus. Looking at the Perseus, I can see the intermodulation signal here, up here, or here, but not as a contribution to a degraded noise floor. So now I can step up the levels 1 dB at a time while looking at the signal-to-noise ratio, the yellow track here, and also with a faster response directly on the screen. So I go up now 1, 2, and the interference disappears. 3, 4, 5, 6, 7, 8, and now it's too strong, the intermodulation. I have lost 6 dB, so I'm back 1, and it takes some time. This is a little more than 3 dB, and I go back once more, and this is less than 3 dB. So here is the point where the degradation is a little bit more than 3 dB, and the signal level is minus 17 dBm. So from this it looks like the Perseus is quite a bit better. And the frequency separation, I'm listening at 13.998 something, and the signal generators are at 13 and 12 megahertz, means 1 megahertz apart. I cannot do the signal-to-noise measurement in the ft1000 anymore, because you can see this peak here has red dots. It means Linrad considers this a spur which is not included in the noise floor. For that reason, I go to the signal generator and say external FM, and you see what happens. I frequency modulate the signal and it's still a strong signal. So maybe I can just make the modulation a little bit wider. Like that. And now I can read the amount of degradation here. About 21 dB. And in the Perseus it's something like 6 dB. And I step up the level 10, and then down. And at this point it's hopeless, there is saturation. So at the point where the Perseus saturates, the ft1000 has big interference, but we can still see the signal here. And I cannot use the S/N measurement because Linrad isn't really written for this. But I can move the pilot tone, the reference, a little bit upwards. And you see we have it here. And I switch off the strong signals. And there is some compression. I think that is AGC, but it could also be compression in the RF chain of the receiver. I don't know. Anyway, now here is totally saturated. But we can hear something, but in the Perseus we cannot. So these radios have very different behavior. I have now moved the strong signals to 20 kHz frequency separation. And then I increase the level until I see a loss in signal-to-noise ratio. And I see it first in the ft1000. This was too much, that's 6 dB. 4 dB. Here is a 3 dB loss. And there is no intermodulation. This is reciprocal mixing. And oops, span 100 kilohertz. And the level here is minus 29 dBm. Now the signal are not exactly equal in level because the notch filter has a small gain variation, and also the low pass filter that I use to prevent from the second harmonic. But this is less than a dB and it doesn't matter for what I'm trying to show. I'm stepping up the level for the Perseus, and first in 10 dB steps. 20, 30, well, that is too much. And this is also too much. But here there is no problem. There is a significant delay through the processing here. So here is the point of 3 dB degradation due to this third order intermodulation. And the signal level here is -9 dBm. That is a big difference. I have connected an antenna now with a lot of amplification, and that is the strong signal that I send through the crystal notch filter. The time is 2:30 in the morning. There is nearly nothing at 14 megahertz, as you can see, but the strong signals here at 9.5 megahertz, and the level in the order of -20 dBm. In the ft1000 I can see something here. If I switch off the antenna signal, you can see that, but it doesn't affect the signal to noise ratio. Now the full signal is there, and I remove it and back again. In the Perseus it's easier to see. The noise floor is pretty strong, and if I remove the antenna signal, you can see like that. But if I look here, you can see the noise floor within the notch does not change. It's an artifact in the spectrum here that the noise floor at the middle of the notch actually changes. It's some smoothing, I don't know how it's done. But if you look at the audio output from the Perseus software into Linrod, you can see that nothing happens when I turn the signal down and then up again. But now I increase 3 dB and wait for a while, and you can see here are problems. Presumably the AD converter now goes into saturation occasionally. And 3 more dB, and it happens more often. And you can see here and in the waterfall. So here the Perseus is no longer very useful, but the ft1000 is not affected. I switch off the strong signal and switch it back on. Look at the signal to noise ratio within the 2 kilohertz I have selected. This is the full power of the antenna signal with maximum amplification, and now there is no signal. So in night conditions the ft1000 is better than the Perseus in this test. And probably it's different in daytime. I will check that tomorrow. Now it's 3 o'clock in the afternoon. Medium waves are dead almost. And we have signals from, what is it, 6 megahertz up to 18. And the marker is at 14 megahertz, and we have fairly strong signals close to the frequency of measurements. And here is what we see on Perseus. And at this level there is no degradation of performance. And the same for the ft1000. But I will increase the level of the antenna signal stepping it up to see where is it, which one is degraded first and how much. At this point there are occasional interferences. You can see something here and something here. I increased the antenna signal by 3 decibels. And we can see problems in both radios. Severe problems occasionally in the Perseus because it's clipping. You can see it's red here and it says ADC clip. So this is too much. I go down 1 dB and now it's not clipping anymore. Well, very rarely 1 more dB. So now this is okay. And the ft1000, you can see it loses 3 dB or so now and then. And you can see here the character of the interference. Here is the audio, and there is something here which is fairly strong. I don't know what that is. So with the daytime antenna signal, both radios can stand the signal level that looks like this, but only a couple of dB above this, then there is a problem. The strongest signal is at minus 12 dBm. This is what the signal looks like on an oscilloscope. There are peaks up to about 1 volt. There was one a little bit above. But most of the time the signal level is 200 millivolts or so. And you can see here, when triggering, not quite as often. So this is the signal that the receivers can take. At this time, what I see here on the Perseus, strong signals, but no, well, occasional ADC clipping. And of course associated problems. And the ft1000 also some loss of signal to noise ratio. So maybe I have to reduce by, let's say, 1 dB. And then the ADC clip happens very seldomly. And the ft1000 looks fine now. Did I say that the oscilloscope is matched to 50 ohms? So it's really the voltage we have in the systems. And here is the antenna. Goes from here, this wire, and up into this tree. It's about 5 meters away. So it's a really bad antenna. I will now change to another one. You can see up here, maybe you cannot see it yet, but you can see the coaxial cable going up. It's a dipole for 20 meters. The gain I have had to apply to saturate the receivers with the simple wire antenna is 37 decibels. So 38 even. So that's the margin I have with this 5 meter long wire before these receivers get non-linear, so I lose sensitivity on them. I now connected the 14 megahertz dipole, and it gives more signal, as you can see here. Both radios are severely saturated. So I bring in some attenuation, 10 dB. That was more than enough. So I bring up signal levels. 1, 2, 4, 5. Here we have problems in the ft1000 and also in the Perseus. 4. Well, something like this, maybe one more. There is a small loss of signal to noise ratio in the ft1000. Well, occasionally there is. And in the Perseus, occasional clipping. Well, I saw one just recently, and you can see here. So these antennas don't make a major difference, but we can see here the spectrum is a little bit different. 14 megahertz marker. Here we have the strongest signals. There are less signals at lower frequencies. And as you can see, on 14 megahertz, the strongest is in the order of -20 dBm. Now this is with a fairly large bandwidth. What does it say? 100 kilohertz bandwidth. So those -20 dBm is several stations at the same time. And here you can see the gain I needed to bring the radios into saturation with the 14 megahertz dipole. It's 28 or 29 dB. So this antenna gives 10 dB more signal to the radios, but still the margin with the tuned antenna is 29 dB. So in this location both radios are seriously overqualified, at least for 20 meters. The oscilloscope looks different on the dipole antenna because the low frequency components are gone and they had the biggest amplitudes. So you can see here the most of the time it is about 200 millivolts peak to peak, but occasionally it is half a volt peak to peak. I have now inserted a filter at 14 megahertz, which is about half a megahertz wide. I can look more in detail here. This is center frequency 14 megahertz and the span is 1 megahertz. And signal levels are, well, at this time about -20 dBm. With the pre-selector, the ft1000 has problems at this level, but the Perseus does not. I add 10 dB more signal now, and there is ADC clip occasionally. This one is heavily disturbed. So that was 10 dB, and I take away 3. well, 4. So it seems with the pre-selector, the Perseus is about 6 decibels better. Here is the Perseus, almost no interference, while the ft1000 has severe interference. Varies a little bit, well, 5 dB maybe on the average, and you can see here what it looks like. With the pre-selector, I have now 43 dB for the Perseus and 37 dB for the ft1000. Without the pre-selector, I had 28. This is the 14 megahertz dipole. So the pre-selector makes a very big difference. These receivers have wideband inputs. I switch off the pilot tone, this one. So now there is only the noise floor in the Perseus at minus 117, and I look at the noise floor outside the notch. And it's at minus 74. The difference is 43 dB. Desirable would be to have 10 dB on HF, maybe 6. Anyway, it means that the margin in dynamic range for the Perseus with the pre-selector in front of it is 33 dB, or maybe 36 or so. So it's a huge margin. Without the pre-selector, the noise floor is at minus 85, and it's the same in the notch, minus 117. So the margin, so the difference in the noise floor from the antenna and from the receiver itself is 32 dB. 10 dB is what is enough for no losses of performance. So there is a margin of 20 dB without the pre-selector. And that's the same for both receivers. I have now connected the loudspeaker to the Perseus. And you can see it's heavily affected by too much signal. And you can see the ADC clipping coming occasionally. But it's not really problematic. The noise blanker is enabled, I think. No, but I enable it. And that's not a very good idea, as you can see. Narrow. That's much better. The transients from clipping can be removed by a suitable noise blanker. I click away that. And here is the loudspeaker output from the ft1000 at the same level. And I remove the antenna signal. Oh, and this is the level where the Perseus has occasional clicking. Now it's severely saturated here, but also here. But it's clear, this is an increase of the noise floor. It cannot be managed by aid of the noise blanker. I think it's essentially reciprocal mixing. This is with the 14 MHz dipole and without any pre-selector. I hope this video has made it clear that this modern SDR, the Perseus, is fairly similar to this more old-fashioned ft1000 when it comes to dynamic range performance on a dipole antenna on 14 MHz. At least in my location. The big difference is that the ft1000 suffers from reciprocal mixing at close range. So if there would be some strong station nearby on 14 MHz, the Perseus would be the winner with a large margin, 20 or 30 dB or something, depending on the frequency separation. I have now connected this IC-706MK2G to replace the ft1000. As it turns out, the signal to noise ratio is about 10 dB better, and that is with preamp off. When I switch in the preamp, it becomes even more sensitive. So it would be unfair to compare with it. I will insert an attenuator to bring it to the same noise figure as I had in the ft1000 and also in the Perseus. A 10 dB attenuator brings signal to noise ratio back to close to 30, where I have been having it during these measurements. I have applied the antenna signal from the 14 MHz dipole, and you can see there is degradation. It varies with time a little bit. I have the attenuators set to 28 dB, and I will change them until I see interference on the Perseus. So here is the Perseus. There is ADC clip occasionally. Well, now it's severe. I had to back off a little bit. At that time, the interference in the Icom was horrible. But at this point, the Perseus has no problems. And the attenuator is set to 22 dB. It might be more instructive to show what happens on the loudspeaker. I increased the antenna signal. This is the Perseus. So this is what we can call a marginal case, and that is 16 dB right now, and it's not so marginal anymore. Now it's 19 dB, so this is roughly where we are. I turn this down and enable the loudspeaker on the Icom, and I had to back off 10 dB, and I can still hear some little noise in the background. Now 20 dB. So that's 10 dB, and now it's 7 dB compared to the Perseus. And this is clearly interference. So this little radio, it's somewhere maybe 7 or 8 or so dB worse than the two other high dynamic range radios. And that is with the 10 dB dummy load in front of the Icom to make the noise figure the same as the other two radios.